Okay, good afternoon, everyone. So, let us start our discussions on the week 11 content. So, let us first start for the block diagram when there is no speed governing action. So, basically, whenever there is in the question, it is given that there is no speed governing action or neglect the governor action. So, that will imply that your delta Pg will be 0. Because if you cannot open or close the valves through the governor control or governor action, that means there will be no change in the generating output of the thermal plant. So that's why the delta Pg will be 0 in such condition. So what will happen is this delta Pg will be 0 and delta PL is your disturbance or change in load, and the transfer function is Kp by 1 plus STP, which we have seen already. That will give you your frequency deviation delta F. So we know that this Kp is 1 upon D. Now whenever there is a load disturbance of delta PL, so in the S domain we can write that the frequency deviation will be minus delta PL into, this is a constant, so 1 by S will come, Kp into 1 plus STP. Now we know that by the method of partial fractions, so we can write this or decompose this into, by using the method of by parts, into two separate terms. And here if you basically equate these two equations, what you will be getting is A is 1 and ATP plus B is 0. So substituting A as 1, you will get B as minus TP. So substituting that quantity here, what I'll get is minus delta PL by S. No, S is gone. So minus delta PL Kp, and in place of 1 by S into 1 plus STP, we will be getting as 1 by S minus TP by 1 plus STP. So we can simplify that as minus PL Kp 1 by S minus divide by Tp in numerator and denominator, so we'll get S plus 1 by Tp. Now if you convert into time domain by taking the inverse Laplace here, so what you will be getting is delta PL Kp, that is in minus, into 1 minus e to the power minus t by Tp. So this can be written in two parts, that is steady state and transient part. So for steady state, we we can put t as infinity, then you will get delta f steady state as minus PL to Kp. So this is for a isolated power system with no speed governing action and no controller. Isolated power system with no controller and no speed governing action. Now let us see what will happen when we add a controller to this. Yeah, so the case of isolated power system with integral control. So previously without the controller, the block diagram was like this. So first we have the governor, followed by turbine model, the turbine, then with the reheater. Whenever 1 plus STR. Finally we get delta PG, and here the disturbance negative, followed by your Kp into Kp by 1 plus STP, that will give delta F. Now we have a feedback here, that is 1 by R, right, and that is your negative feedback, so minus. Now what we do that, in addition to this we add a PI controller block here, so its transfer function is minus K by Ki by S, and this delta F is coming here. So here also we are adding that negative integral control box. That means here Ki is greater than 0, so that this whole is negative. Then only the system will be stable. If you give positive feedback, as you know, the system will drive to unstable condition. So that is the rule here, right? So what happens when we add this additional controller, PI controller, not PI, only integral controller here. So if you like write the expression of delta F from this block diagram and then substitute your S is 0 for steady state condition. So finally what we get is, for such a system with a controller, your delta F steady state becomes 0. That means whenever there is a disturbance, so initially there will be certain oscillations, but then it will settle to 0. So this is your delta F. Now this U steady state will be same as your change in load, that is delta PL or PD here, PL. So let's say delta PD is here. So that means it will also settle down at delta PD after some time, and delta PGSS is also equal to delta PD. Delta PG that will be same as your U. Now let us see the composite frequency response characteristics. Composite frequency response characteristics. So earlier we had just one generator. So now we'll have multiple units connected in parallel. So the block diagram will be such that this is your first unit, first governor, 1 by 1 plus STG1, then first turbine 1 plus STT1. Let's not neglect the reheater model. Then what you will be getting here is delta PG1. Similarly, we'll have second one, then second governor, second turbine, and this output PG2, delta PG2. Similarly, you can have up to N. U1N, so that will give you delta PGN. Now we'll add the load disturbance here, minus PL Kp into 1 plus STP. That will give you your delta F, and each will have their feedback, that is 1 by R1, 1 by R1 negative, similarly here also 1 by R2, and here also you'll get 1 by Rn similarly. So this completes your block diagram for the frequency response characteristics and when there are more than one generating units. So for uncontrolled system, so this u will be 0. U11 of all units for all units, right? And we already know that at steady state, this delta Pg1 steady state is minus delta F by R1. Similarly, for unit 2, delta Pg2 minus delta F SS by R2, and similarly up to nth unit. Right. Now, this relation, if you add, basically steady state means here the S will be 0 for steady state. So what will happen is all these blocks, they will reduce to 1 at steady state. So from that you will get this relation basically, and we are writing this delta F steady state expression. So you can see it here, right? So if we do that, so plus delta Pj 2ss plus delta Pgn ss minus delta PL into Kp is equal to delta F steady state. Basically at this node we are writing, so sum of all the generations, this Pg1, Pg2 and Pgn minus PL, that is input to this. Here again S is 0 means this will be Kp at steady state. So this multiplied by Kp is your delta F steady state. And we know that Kp is nothing but 1 by D, right? So substituting that, so I'll get, and Pg steady state also, let us substitute from the above here. So delta Fs by R2 minus delta Fss by Rn minus PL equal to D times delta Fss. So from here you can get delta Fss as minus PL divided by all these coefficients of delta Fs, that is D plus 1 by R1 plus 1 by R2 up to 1 by Rn. So that we write in compact form as D plus 1 by R equivalent. Where your this R equivalent is nothing but 1 by 1 by R1 plus 1 by R2 to 1 by Rn. So this was for your uncontrolled system. Now let us add the integral controller to the system. So what will happen is, so we had seen, right, this u, before this u we'll have the I integral controller. So we'll see that. Just a second. Yes. So now we'll see it with integral controller, controlled system. With integral control. So another feedback here with the integral controller. U, and that will be passed through some weights A1, A2, An. So we'll discuss what these weights mean, why we add this. Right. So this A1, A2, An, so they are called as your participation factor. So let's say whenever there is a disturbance of, let's say, 10 megawatt, and let's say there are three generating units. So what will happen is this delta Pg1 plus delta Pg2 plus delta Pg3, that will be equal to your PL, right? Because we have the integral control action, so we had seen that this sum is exactly equal to change in load in this case. Now what will happen is, so all these three generators, they will share this load disturbance, but how much which generator is going to share, that will depend upon their economic characteristics. So you know that thermal plants, so they have their own cost function or fuel characteristics. So they can be sometimes written like this: A time Pg square plus B time Pg plus C. So these are your cost coefficients ABC, and depending upon this, you can tune such that the cheaper generator we'll have, we can say, greater participation factor, so that the load change can be satisfied using the most economical control action. Most economical control action. And this A participation factor basically, so it will lie between 0 to 1, and all this summation AI, so I belongs to all your generators, should be equal to 1. Okay, so your delta Pg1 steady state will be A1 times delta PL, delta Pg2 will be A2 times delta PL, and so on. So this is clear, I think. Now let us see what is a control area. Okay, no problem. So control area. Basically, it means that it is one area with, let's say, many generating units, and this area A1, in this area, in area A1, a common generation control scheme is applied. Is applied, right? So all the generators in this area, they are swinging, we say, in cohesion or coherently, which means that they have a single frequency. Now, for two control or two or more control areas which are interconnected with each other, let's say you have three control areas, like this, right? So there are two possible cases. So case 1 is when the system frequency is according to schedule. So that means whenever there is a disturbance, let's say delta PD3 here in area 3, so generator in area 3 will respond to it, will respond to delta PD3, and they will regulate the frequency here. So that in this case 1, our main aim is that this tie line power should be maintained according to the schedule. So delta P tie is 0, or your P tie line is maintained at the schedule power, which means that whenever there is a disturbance within the system, only the generators in that system will respond to the disturbance. Other area generators, they will not respond to it. So that is one case. For the second case, what happens is, so again, let's say delta PD3 disturbance is there, but now the generators in area 3 are not able to regulate the frequency, which means that this sum of delta Pg3 means all the generators in area 3, that they are not equal to the disturbance PD3 for some reason, let's say. So in such case, what will happen? The frequency will change, which means it will be not at the scheduled. So whenever the schedule frequency will change, the generator in remaining areas will respond to this change in frequency, and they will shift their power so that the tie-line power will change in accordance with the change in frequency to restore the system frequency. So how much each tie line power will be changed, or the extent to which the P tie will change for different area, will depend upon the frequency bias setting. Will depend on the frequency bias setting. Okay, so we'll see those in the questions. Now let us discuss the assignment. Okay. So question 1 is area control error ACA in a multi-area power system reflects A is the change in mechanical power input. C is the Thailand power, sorry, B is the load power imbalance. C is the Thailand power imbalance. D is none of the above. So what will be the answer here? Area control error we have not. Multi-area power system basically we'll discuss in the next week because most problems for that are in the next week. So briefly what I can say this area control error, it is directly related to the imbalance in the load. So we'll see it in the next week in detail. The second question is the objective of secondary frequency control is to change the frequency, change the PF troop, change the reference power, D is none of the above. So can you tell what is the answer to this? You can write in the chat box also. So the PF troop, we know that that was in your primary control, right? So the secondary control, what you do is basically you change the reference power. correct action is C. Now next question. So a frequency sensitive load connected to a 60 Hz power system changes by 1.25% for 1% change in frequency on 500 kVA system base. So if the system base is changed to 1 MVA, calculate the value of D per unit megawatt per hertz So here basically first the D is per unit change in load per percentage change in frequency. So percentage change in load divided by percentage change in frequency. So here it is written that the how much 1.25% change in load is there for 1% change in frequency. So 1.25 for 1% change in frequency. So here the how much the like this is 1% of your 60, so 1.25% of your 500 kVA load, right? This is hertz. So if I write it in megahertz into 0.5 megawatt divided by 1 into 60 hertz, right? So this is kilowatt. Now for converting into per unit, the system base is given as 1 MVA, right? So that will be 1.25 into 0.5 divided by base, which is your 1 divided by 1 into 60. So now this is in per unit, this is in hertz. So that will give you as 0.01042 per unit megawatt per hertz. This is your answer. Now next question is, so a 60 hertz small system consists of 5 identical 400 kVA generating units feeding a total load of 1 megawatt. The inertia constant H of each unit is 6.0 on 500 kVA base. The total load varies by 10% for 1% change in frequency. The speed regulation characteristics, that is R is 1. When there is sudden increase in a load of 100 kilowatt, find the steady state frequency in hertz, assuming that speed governor loop is inactive. So this question, you system load PL, so feeding a total load of 1 megawatt is given. So 1 megawatt and the total load is, increase in load is 100 kilowatt, right? Plus 100 kilowatt. So that will give us 1.1 megawatt. Now let us calculate this D. So D we had seen, that is percentage change in load by percentage change in frequency. So here it is given load is varying by 10%. So 10% of what? Of 1.1, right? So 1.1 for 1% change in frequency. So frequency is 60. So that will give you as 0.1833 in megawatt per hertz. Now no governor action is there. So that means we had seen whenever there is no governor action means delta Fs was minus PL by D, or it was Kp if you remember. We had derived this. So Kp is 1 by D. So this is your steady state frequency deviation. So how much there is increase in load, so delta PL will be positive. So 0.1 and D is 0.1833. So this is in megawatt. This is in megawatt per hertz. So finally we will get this as minus 54546 megawatt will cancel out. So this will be in hertz. So finally your F steady state will be F naught plus delta F steady state. So F naught was 60 minus 0.54546, that is giving us 59.4545 hertz. So this is when you don't have the governor action. Okay, I hope this was clear. Now next question is, so it is same as above, same as question 4, but here it is asked that when there is a sudden increase in load, in a load of 100 kilowatt, find the percentage improvement in the steady state frequency obtained after activating the speed governor loop with respect to the steady state frequency obtained without this governor action. Without the speed governor loop. So without, we have seen without governor, your delta FSS was minus 54546 and your finally F steady state was 59.4545 hertz. So we'll see what will be with governor. So whenever there will be governor means the speed regulation feedback will be activated. So that R, it was given as how much R is 1 hertz per unit megawatt. So it is 1 hertz per unit megawatt. So if I convert it into hertz per megawatt, so how much is your system base? This that was, yeah, it is 500 kVA base, right? So that means that will be megawatt. That will give us 0.5 hertz per megawatt. And now delta F steady state with governor will be minus delta PL. Earlier it was D. Now speed regulation will also come. So earlier delta PL was zero point 0.1 megawatt, and D we had calculated it was 0.1833, right? Yes, megawatt per hertz, and R is 0.5 hertz per megawatt, which means it will be 1 by R is 2 megawatt per hertz. So that will give us minus 0.045802 hertz. So F steady state with governor will be 60 minus 0.045802, which is giving us 59.9542 hertz. So percentage improvement you can calculate as 59.9542 minus 59.4545 divided by 59 by 4545 into 100. So that gives us as 0.8405% improvement. Now next question. So the speed regulation characteristics of two generators connected in a power system are as follows. Generator 1 100 MVA, 50 Hertz, speed regulation is 0.02 Hertz per unit megawatt on machine base. and generator 2 is 120 MVA T-hertz, R2 is 0.005 hertz per megawatt. So if two generators are connected in parallel, the equivalent speed regulation R in hertz per unit megawatt of two generators on 100 MVA system base is. Okay, so this is very simple. Can you tell how to proceed for this? R equivalent we need to find out, right? So R equivalent we had seen it was 1 by R1 plus 1 by R2. Now R1, it is given as 0.02 hertz per unit megawatt. So now it is asked that on 100 MPa system base. So divide by 100. So hertz per megawatt, it will be 0.0002 hertz per megawatt. And R2 is already given in hertz per megawatt, 0.005 hertz per megawatt. So R will be 1 by 1 by R1 plus 1 by R2. That will give us 1 by, so 100 by 0.2 will be 5000, and similarly this will also be 200. So that will give 0.001923 hertz per megawatt. So 100 MVA is base. So if you multiply that, basically you will get 0.01923 hertz per unit megawatt. Now question 7. So consider a two-area system connected with a lossless tie line with speed regulation R1 is 0.03 per unit and R2 is 0.045 per unit and damping factor D1 is zero point 0.9 per unit and D2 is 0.6 per unit. So base VA of each area is 100 MVA. So area 1 is subjected to load increment of 9 megawatt and area 2 is subjected to a load decrement of 12.5 megawatt. Find out the steady state frequency deviation given the nominal frequency is 60 Hz. So no control actions. Here two areas are given. Area 1, area 2. So here R1 is 0.3, here R2 is 0.45, D1 is 0.9, D2 is 0.6 and area 1 is increment of load 9 megawatt and delta PD2 is decrements minus 12.5 watt. So let us calculate that. Delta PD1 will be 9 megawatt or the base is 100, so 0.09 per unit. So here increment we take as negative and decrement is 2.5. Minus 9. Generally delta PD2 is 12.5 or 0.125 per unit. So this frequency bias setting that we had seen, it was composite load. So it will be D1 plus D2 plus 1 by R1 plus 1 by R2. So that will be 1.5 plus 1 by R1 plus 1 by R2, which is 57.05 0.55 per. Now steady state frequency deviation is minus delta PL by beta. So that is minus of 0.09, 0.125 divided by beta. So you will get this as minus of 0.00613 per unit hertz. 0.00613. So into 60 will give you in hertz, which is minus 0.03681 hertz. Question 8 is, so it is same as 7, but here find out steady state tie line power flow in megawatt. So delta Pg1 is minus 1 by R1 delta F minus 1 by 0.03, and delta F we had calculated. So this is in per unit. So that delta F also will put in per unit. 34 per unit. So which will give you as so at steady state, so delta Pg1 minus delta PL1 minus P tie from 1 to 2. So 1, 2. So this is the direction 1 to 2. Power is from 1 to 2. So here it will come as minus P tie 1 to 2. So that is D1 times delta F. So delta P tie 1 2 is delta Pg1 minus delta PL1 minus D1 delta F. So this is 0.2045, and here it was 0.09. D1 is 0.9 and delta F is minus 0.006134. So this you will get as 0.111002 per unit. So 100 MVA base, so it is 11.1002 megawatt. Now question 9. So for a isolated generating station with local load, so a block diagram is given in figure. Delta PL is minus 0.15 per unit, brings delta omega as 0.25 per unit in steady state. Find R in per unit. Take delta PC equals 0. So this is the block diagram given. Delta PC plus 1 by S plus 1 delta PL 10 by 1 plus 10S delta omega 1 by 1. So for first question, delta PC is 0. So here I will get as delta omega is equal to, so here delta omega will come here, this point, right? So delta omega into minus 1 by R, and PC is 0 here, so here again it will be multiplied by 1 by S plus 1. So this minus PL. So this minus delta PL, again it is multiplied by 10 by 1 plus 10S, that is your delta omega. So from here delta omega will be 1 by 1 minus 10 by 1 plus 10S into minus 1 by R into 1 by s plus 1 whole multiplied with 10 by 1 plus 10s into delta PL. So at steady state, s tends to 0. So delta omega will be 1 by 1 minus 10 minus 1 by r 1 into 10 delta PL. So delta omega is given as 0.25 is 10 into delta PL, 10 into minus 0.15 is 1 plus 10 by r. So 1 plus 10 by r is equal to 10 0.5 it is minus 6 or 10 by r is minus 7 or r is 10 by 7. So here actually minus is coming. So minus this is minus 6. 10 by r is 5. So r is 2. Question 10. So same only minus 0.15, 0.25, same as 9. So specify the value of PC, delta PC to bring delta omega to 0. So delta omega was From there you can see it was minus 1 by r delta omega. So up to here minus 1 by r delta omega. Now plus pc will come here, plus delta pc into 1 by 1 plus s. So you are here now minus pl minus pl whole into 10 by 1 plus 10s. Okay, so rearranging the terms, you will get delta omega as 10 by 1 plus 10s divided by 1 minus 10 by 1 plus 10s into minus 1 by r 1 by 1 plus s into 1 by 1 plus s delta pc minus delta pl. So at steady state s tends to 0, so delta omega is 10 by 1 plus 10 by r, and here it is delta pc minus delta pl. So delta omega we need to bring to 0 is 10 into delta pc minus delta pl 1 plus 10 by r, which means delta pc is same as delta pl, which was minus 0.15 per unit. So this is the end of this week's assignment.